Good morning all. Welcome to our webinar, The Breakfast with MSA. This is our breakfast. And we are today at topic number possible. And what we are asking about is if it is at all possible to have a systematic error of a measuring device equal to 0. All right, just a reminder, this webinar is part of the series of the measurement system analysis. We are at topic number 5. We are at the half of these webinars. And the English version is running every second Tuesday in the month. In the morning, I should say, of the Central European time. Very well, let me share my favorite whiteboard. So we can start right away. The first thing I wanted to mention is that there are certain classifications of the measurement errors. There are different types of these classifications, and the one that we should keep in mind today is the distinction between the random and systematic error. When it comes down through the measurement uncertainty, we treat all the errors in the same way. We estimate the standard uncertainty, and then we calculate with all of them in the same manner. But specifically for bias, it's necessary to realize that it is the systematic part which can be compensated. Unlike the random error, which does not have a simple compensation in the way of addition or subtraction. So what is the bias? If we only have one part and the part has a dimension corresponding to this red dashed line, usually this is denoted as an XM, or sometimes it's not exactly the same thing, but very similar concept, X star. And then we would make a series of repeated measurement of the same part. We would get these little blue dots. These are the individual measurements, either in time, that's the T, or just in the order of n from 1 to whatever number. And then this set of measurement in the ideal world would have its dispersion. That's this green thing. That would be the repeatability. EV, equipment variation. And then this region would be systematically shifted from the true or precise dimension of the same part. It will be systematically shifted from the red line. And this shift is what we call the bias. All right, so now we had just one part. How about if we generalize that for more? Let's go for 2. With 2 parts up here in the corner, the situation may be that the shift is different in different parts of X. With the first part, the shift is down, but with the second part, the shift is up. And this suggests what is very usual in the measuring devices, that the bias, the systematic error, has different values at different points of the measuring scale. So we make a different type of a representation. On the horizontal axis, we'll put the precise dimension, the xm, and on the vertical axis, as a functional point, we would make the repeated measurements. And they are dispersed here. The dispersion really is not there. Let's imagine this is just for the graphical purposes. They all lie on the vertical red line. With this representation, the green equipment variation is now, green equipment variation is now the span of the yellow region. And the bias is the difference between the center of this highlighted region to an ideal line, that's the thin one in the middle. The green one, the blue thin line in the middle is exactly where the measurement equals the reality. So the bias, here in red, is the vertical measure between the ideal state and the center of the region of repeatability. In this case, if we have exactly two measurements, then we can connect these two regions with the yellow line. With this switch, we are now in the realm of linearity. And as you can see, with this yellow line, if it goes through the centers of the regions, through here and here, it compensates for the bias exactly. So, and this is the answer to the question posted in the beginning. This is the answer to the question, which is the name of today's topic. How is it possible to have a bias equal to 0? Well, one thing is that if we only observe two measurements, then there always is a point right here where the bias is exactly 0, just because of the concept of the line. And unless the lines are parallel, there always is such a point. Well, even if they are parallel, they'll connect in the infinity, but that's not really interesting to us. So in cases like that, we would switch the bias to linearity. The linearity then would be the maximal error on the edge of the tolerances. And if we don't have the tolerances, it would be the biggest one on the edge. If we have just two, it would be the bigger of these two biases. This will switch to linearity. And if we do the switch, then the bias will equal to 0. And before we'll show you that in Yarvin, how this is realized in the actual measurements, I need to make a little reminder. Here I am presenting two parts with known dimension, and that is the case for absolute measurements, where we with every part with known dimension, we can estimate what is the bias, because in absolute measuring devices, the device does not need the reference to sort of calibrate itself or set itself. On the other hand, in production measurements, many of the measuring devices need some kind of a master, a reference on which they set, and only then they know where is their zero. Basically, it is if the device has its own zero or if it gets the zero from the reference. And in that case, it does not really make sense to make this repeated measurement on the master on which the measuring device was set, because there is only another view, it is another take, as it's written here, on the repeatability, and not actually on the bias. And Martin, please show us how this is done in Arvin.
Good morning. So I will share my screen. And in Arvin, it works another way. Everything in Arvin is connected to the experiment you will make, and how this experiment is designed, because the results you can get from the Arvin, from the calculations, really is dependent about the number of masters you have. So there are several options that are possible. First option, and that's this case, I have lots of masters. In this case, it's I think 10. Yes, I have 10 masters. So everything can be calculated directly from the data. If we just check the experiment, you can see I have 10 masters, some measured values for each master. And if we go to results, you can see that the bias is calculated as type A uncertainty, and the linearity is also calculated as type A. That means that both of these values are calculated directly from the data. That's first case. Second case is the special one when I have exactly 2 masters. Because as Jaroslav told you, in this case, when you try to imagine how linearity works, it always is some difference between some ideal linearity, some ideal line, and the line that is intersected across your measurements. And if you have 2 masters, we can say that every line that you can intersect across your measurements is ideal. So that means that if you go back here, the bias cannot be calculated in this case, or it's 0. And linearity is calculated as type A uncertainty. Another option is if you have only 1 master. You can see I have only 1 master. This is comparative measurement, so I need another adjustment master. I will talk about this a little bit later. But when I have only 1 master, of course, there is no chance I can calculate the linearity from the data. So if we go to the results, you can see bias is calculated as type A uncertainty. And if I need some information about linearity, it has to be added as type B uncertainty. So in this case, it's a combination of type A and type B. Bias is type A, it's calculated from the data, and linearity is type B, it's from the B-type uncertainty. Can be at something like this, for example. Yes, and then I have both results. For the comparative measurements, it's a little bit complicated, but only just a little bit. And the complication is what Jaroslav said, we need another master, something that is called the adjustment master. And it means that for all the cases I mentioned, it means I need this master. I need to add this master to the experiment. So for the comparative measurements, if I have two masters, I can calculate the bias from the data, and linearity has to be at as type B. If I have this configuration, two masters and one adjustment master, this is the special case where I cannot calculate bias, or it will be 0. And let's say full setup or the setup that I get all the results calculated from the data as type A uncertainty is this one, when I have three masters and one adjustment master. Yeah, so for the comparative measurement, I need always one master's add to the experiment. And this is how it works, how you can set up the experiments, and according to these setups, according the number of masters you have, it depends what results you get and what type of uncertainties it will be. So that's everything from this, and we can go back to Jaroslav.
Thank you very much. And so this was basically it. And let me summarize how this is done, and with the experiment Martin has just described with the full setup, and what this full setup actually means for the measuring device. So let's imagine that we will generalize it more from two masters in this slide to several masters in the last one. Let's say these A, B, C down to F are the individual masters. They have their real or believed dimension, the calibrated dimension. And for each one of those, we will do repeated measurements. And we can estimate approximately what the results of these experiments will be by these means. Let's say the measuring device has its equipment variation, some random error represented here by the width of the green region. Then, on top of that, it would have the systematic error, and the systematic error is the wavy blue line, sorry, wavy green line, I believe it's green, in the middle of this green region. And that's the systematic error. And because that's the tradition and practical approach in the metrology, this systematic error will be divided in between the linearity, and that is anything what can be compensated by a straight line, which can be inclined and shifted, so two parameters, and everything what remains. So the thick green line with that blue highlighted region is what is compensated by the linearity. So the linearity is an abstract concept. It does not say that the only systematic error can be compensated by line, but it is the practical division. And then something remains, And what remains is the distance between the green line and the center of the wavy line. So the linearity together with bias is the systematic part of the error. So if we put these ABCs into the measuring device, let's say this would be A, then from the ideal dimension, which would be here on the center of the, on the axis of the quadrants, the 45-degree line, the actual measurement will first shift by the linearity, then it will shift again by what remains to the wavy line, and then it will generate a random value within the equipment variation region. So we may end up with, let's say, this little value. And if we do that repeatedly, then the idea is that we would be generating from a distribution with a center at the thin green line, the center of the wavy region, but not that much far away from that center. The further we would go, the lower the probability. So the blue dots will likely be somewhere here, only a few times out of this region. And this would be the case for all the different cases that we may have here from A to F. It is good to include references that are out of tolerances. And the reason for that is that we don't need the measuring device to be very good only within the tolerances, especially when things go bad, especially when the production reaches out of the tolerances, that is the case where we need to have a good measuring device to shift us back on the track. So we need to make sure that the measuring device is also proficient, that it also can measure very well on the edges of the tolerances and even beyond. Well, with that, we only have a few masters to measure. We don't have a continuity of masters to measure. So we will only estimate this region, then this region, then the A I already have here. With C, we would have this region. So you can see that the systematic error is only sampled. And this is something to be considered when we are picking up all these masters. This is something we should keep in mind. Usually this is neglected. We just want these to be distributed. If they are evenly distributed or not, it does not really bother us. But well, we need to have some simple approach. We work in industry, so we cannot have everything precise. The having more than two, having three, is the least minimum to have an idea what this systematic error, the linearity and the bias is. The recommended number is 5. And the more you have, the better you'll know what the linearity is, but the more expensive the experiments get. So this is a wager that everyone has to solve for themselves, depending on the case. I would say that approximation from a few points is not a big compromise. it's something we can live with very well. And if you feel that the overall systematic error is underestimated, that you may be lucky enough to get exactly something what is in the center. Let's say we would have a master right here. Let's call it D. Then you always have the possibility to add a B-type uncertainty, which would reflect that. You can enlarge the uncertainty per your discretion. All right, that was the topic for today. It was in many ways repeating what we had in some of the previous webinars. The reason for that was to conclude this part, because the next time we will enter the realm of measurement process. So far we've been talking about the measurement system, and next time we'll go for the measurement process, specifically for the experiment on measurement process influences. Very good. We still have some time. Are there any questions? I don't see none, neither in the chat nor in Q&A. So if you have any questions, please let us know. Write us an email. We'll be happy either to answer you or to address your topic in the next webinar or in one of the next webinars.
We are here to work real hard.
That's it for today. Thank you very much, and I'm looking forward to see you the next time.
Deary bet, we are deary bet. Deary bet, we are deary bet. Deary bet, we are deary bet. We are deary bet.